OK, so now we're going to change topics and start talking about our first technical subject of this course. And as an introduction to computer architecture, we're going to be talking about what is architecture versus microarchitecture. And I wanted to just briefly say that as you take this class, the first 3 lectures or so should be review. So if you sitting in the class and you're saying, oh, I've seen all of this before, don't get up. Wait to the 4th or 5th lecture, and then the content will become new. And this is because I want to teach everything from first principles and get everyone up to speed. But those first 3 lectures are going to go very fast. So if you're lost in the first 3 lectures, which should be review, then that's probably a bad indicator. So we'll start off by talking about architecture versus microarchitecture. And I wanted to say briefly what I mean by architecture. And I have in this slide here a very large A for what I'll sometimes call big A architecture. So Patterson and Hennessy calls this instruction set architecture. And I want to contrast this with microarchitecture, or what Patterson and Hennessy calls organization. So big A architecture is an abstraction layer provided to software, or instruction set architectures are abstraction layer provided to software, which is designed to not change very much. And it doesn't say, it says how a theoretical fundamental sort of machine executes programs. It does not say exactly the size of different structures, how fast those things will run, the exact implementation issues. That falls into organization. And one of the things I wanted to emphasize is that computer architecture is all about trade-offs. So when I say it's all about trade-offs, you can make different design decisions up here in the big A architecture or the instruction set architecture, and that'll influence the application, it'll influence the microarchitecture. But also, you can make different design decisions down here and make a lot of different trade-offs on how to go about implementing a particular instruction set architecture. And largely, when you go to look at computer architecture and computer architecture implementation, the design space is relatively flat. There's sort of an optimum point where you want to be, but the other points around it are many times not horribly, horribly bad. Though there are, at the extremes, probably horribly bad design decisions. But a lot of different design points are equally good or close to optimal. And the job of a computer architect is to make the very subtle design decisions around how do you move around this point to make it both easier to program, lives on for many years, is low power, and sort of other a little bit of aesthetic characteristics mixed together with just making your computer processor go fast, we'll say. And these trade-offs, I will reiterate this over and over again in this class, that because there's multiple different metrics, so for instance, speed, energy, cost, and they trade off against each other, many times, and there is no necessarily optimal point. It depends on, if are you more cost-driven or energy-driven or speed-driven. And within that point, there's sort of sometimes Pareto optimal curves where all the points are equally good if you're trying to trade off these different things for different cost models. OK, so let's talk about what is a instruction set architecture and what is a microarchitecture. So a instruction set architecture, or big A architecture, is trying to provide the programmer some abstract machine model. And many times, what it really boils down to is it's all the programmer visible state. So for instance, how does the machine have memory? Does it have registers? So that's the programmer visible state. It also encompasses the fundamental operations that the computer can run. So these are called instructions. And it defines the instructions and how they operate. So for instance, add. Add might be a fundamental instruction or fundamental operation in your instruction set architecture. And it says the exact semantics on how to take one word in a register and add it to another word in a register and where it ends up. Then there's more complicated execution semantics. So what do I mean by execution semantics? Well, if you just say adds take two numbers and add them together and put them in another register, that many times does not encompass all of the instruction set architecture. You'll have other things going on. For instance, I/O, interrupts, and you have to define in your instruction set architecture or your big A computer architecture, what is the exact semantics of an interrupt or a piece of data coming in on an I/O? How does that interact with the rest of the processor? So many times the instruction execution semantics is only half of it, and what we have to worry about is the rest of the machine execution semantics. Big A architecture has to define how the inputs and the outputs work. And finally, we have to define the data types and the sizes of the fundamental data words that you operate on. So for instance, do you operate on a byte at a time, 4 bytes at a time, 2 bytes at a time? How big is a byte? Do you actually have bytes? So this gets into sizes. And then data types here might mean that you have other types of fundamental data. So for instance, the most basic one is you have just some bits sitting in a register in your processor. But it could be much more complex. So you could have, for instance, something like floating point numbers, where it's not just a bunch of bits. It's bits formatted in a particular way and has very specific meaning. It's a floating point number that can range over, let's say, most of the real numbers. OK, so in today's lecture, we're going to step through all these different characteristics and requirements of building an instruction set architecture. And I wanted to, and we'll talk about how it's different than microarchitecture or organization. So let's think about some examples of microarchitecture and organization. So what microarchitecture and organization is really thinking about here is the trade-offs as you're going to implement a fixed instruction set architecture. So for instance, something like Intel's x86 is an instruction set architecture. And there's many different microarchitectures or implementations. There's the AMD versions of the chips, and then there's the Intel versions of the chips, and even inside of, let's say, the Intel versions of the chips, they have their high-performance version for their laptop, which looks one way, or high-performance version for, let's say, a server or a high-end laptop, which looks one way. And then there's another chip for tablets. Intel's trying to make chips for tablets these days, and they have their Atom processors. And internally, they look very different, because they have very different speed, energy, cost trade-offs. But they will all execute the same code, and they all implement the same instruction set architecture. So let's look at some examples of things that you might trade off in a microarchitecture. So you might have different pipeline depth, numbers of pipelines. So you might have one processor pipeline, or you might have 6, like something like the Core i7s today. Cache sizes, how big the chip is, the silicon area, what's your peak power, execution ordering. Well, does the code run in order, or can you execute the code out of order? That's right. It is possible to take a sequential program and actually execute later portions of the program before earlier portions of the program. That's kind of mind-boggling, but it's a way to go about getting parallelism. And if you keep your ordering correct, things work out. Bus widths, ALU widths. If you have, let's say, a 64-bit machine, you can actually go and implement that as a bunch of 1-bit adders, for instance. And people have done things like that in the microarchitecture. And this allows you to build more expensive or less expensive versions of the same processor. So let's talk about the history of why we came up with these two differentiations between architecture and microarchitecture. And it came about because software sort of pushed it on us and ended up being a nice abstraction layer. So back in the early 50s, late 40s, you had software that people mostly programmed either in assembly language or machine code language. So you had to write ones and zeros, or you had to write assembly code. And sometime in the mid-50s, we started to see libraries show up. So these are sort of floating point operations were made easier. We had transcendentals, those are the sine, cosine libraries. You had some matrix and equation solvers. And you started to see some libraries that people could call, but people were not necessarily writing code by themselves or writing large bodies of code in assembly programming because it was pretty painful. And then at some point, there was the invention of higher level languages. So a good example of this was Fortran. Came out in 1956. And a lot of things came along with this. We had assemblers, loaders, linkers, compilers, a bunch of other software to track how your software is being used even. And because we started to see these higher level languages, this started to give some portability to programming. It wasn't that you had to write your program and have it only map to one processor ever. And back in the 50s, even 60s timeframe here, machines required experienced operators who could write the programs, and you got these machines and they had to be sold with a lot of software along with them, so you had to basically run only the software that was given, because you had to be a master programmer or someone who worked for the company that built the machine to even be able to program these machines back in the day. And the idea of instruction set architectures and these breaking the microarchitecture from the architecture didn't really exist back then. And back in the early 60s, IBM had 4 different product lines. And they were all incompatible. So you couldn't run code that you ran on one on the other. So to give you an example here, the IBM 701 was for scientific computing. The 1401 was mostly for business computation. I think they even had a second one that was sort of for business, but different types of business computation. And people sort of bought into a line, and then as the line matured and developed, they had to either rewrite their code or they had to stick into one line. But IBM had some crazy insights here, is that they didn't want to have to, when they went to the next generation of processor, they didn't want to propagate these 4 lines. They wanted to try to unify the 4 lines. But one of the problems was these different lines had very different implementations and different cost points. So the thing you were building for scientific computing wasn't necessarily the thing you want to build for business computing. And the one that you built for business computing, let's say, you wanted to not have it have very good floating point performance. So how do they go about solving this? And their solution was they came up with something called the IBM 360. And the IBM 360 was probably the first true instruction set architecture that was implemented to be an instruction set architecture. And the idea here was they wanted to unify all of these product lines into one platform, but then implement different versions that were specialized for the different market niches. So they could they could unify a lot of their software systems, unify a lot of what they built, but still build different versions. So let's take a look at the IBM 360 instruction set architecture, and then talk about different microarchitectures that have been built of the IBM 360. So the IBM 360 is a general purpose register machine, and we'll talk more about that later in this lecture. But to give you an idea, this is what the programmer saw or what the software system saw. This isn't what was actually built in the hardware, because that would be a microarchitecture constraint. But the processor state had 16 general purpose 32-bit registers. It had 4 floating point registers. It had control flags, if you will. It had condition codes and control flags. And it was a 24-bit address machine. And at the time, that was huge. So 2 to the 24 was a very large number. Nowadays, it's not so large, and they've since expanded that on the IBM 360 successors. But they thought it was good for many, many years, and it was good for many, many years. And they defined a bunch of different data formats. So there was 8-bit bytes, 16-bit half words, 32-bit words, 64-bit double words. And these were the fundamental data types that you could work on, and you could name these different fundamental data types. And it was actually the IBM 360 that came up with this idea that bytes should be 8 bits long. And that's lived on for today. Because before that, we had lots of different choices. There was binary coded decimal systems where you actually would encode a number between 0 and 9, and then you had each digits, and this is sometimes good for sort of spreadsheet calculations or business calculations where you want to be very precise on your rounding to the penny. And sometimes bit-based things don't actually round appropriately, or you'll lose pennies off the end. And so you had these binary code decimal systems, and well, in the IBM 360, they unified it all and said, well, no, we're going to throw out certain things and make choices. Now they, of course, because it's the IBM 360 and they did have business applications, they still supported binary coded decimal in a certain way. And let's look at the microarchitecture implementations of this first instruction set architecture. So this is in the same time frame, the same generation here. There was the Model 30 and the Model 70. And this was very, very different performance characteristics. So if we look at the machine, let's start off by looking at the storage. The low-end model here had between 8 and 64 kilobytes. And the high-end model had between 256 and 512 kilobytes. So very, very different sizes. And this is what I'm trying to get across here, is that microarchitecture can actually change quite a bit, even though the architecture supports 64-bit adds and additions, you can actually implement different sized data paths. So in the low-end machine, they had an 8-bit data path. And if it wanted to do a 64-bit operation, it had to do 8-bit operations to make up a 64-bit operation. And probably it actually even had to do more than that to handle all the carries correctly. Versus the high-end implementation had a full adder there, and it could actually do a 64-bit add by itself without having to do lots of micro-sequenced operations. And, oh, yes, with minor modifications, it lives on today. So this was designed in the 60s, and even today, we still have System 360 derivative machines. And a piece of code you wrote back in 1965 will still run on these machines today, which is pretty amazing, natively. So how does this survive on today? So here's actually the IBM 360 47 years later, as in the Z11 microprocessor. So the IBM 360 has since been renamed to the IBM 370, and then it has been renamed to the IBM 370EX, which was in the 80s. There was never a IBM 380, strangely enough. And then later on, they just changed the name to the Z series. So have a cooler model numbers here. So we had the IBM Z series processors, and this lives on today. So going back to that 8-bit processor, which had a 1 microsecond control store read, which is forever, we now have the Z11, which is running at 5.2 gigahertz, has 1.4 billion transistors. They have updated the addressing, so it's no longer 24-bit addressing, but it still supports the original 360 addressing. It has 4 cores, out-of-order issue, out-of-order memory system, big caches, on-chip 24 megabytes of your L3 cache, and you can even put multiple of these together to build a multi-processor system out of lots and lots of multi-cores. And what I'm trying to get across here is that if you go forward over time and you build your instruction set architecture correct, it can live on, and you can have many different microarchitecture implementations and still leverage the same software. And a few more examples just to reinforce this a little bit more. Let's take a look at an example of something where you have the same architecture but different microarchitectures. So here we have the AMD Phenom X4. And here we have the Intel Atom processor, the first Intel Atom processor. And what you'll notice, actually, is that they have the exact same instruction set architecture. They both run x86 code. And the design implementations, and this is just to point out here, these are the same time frames. So this is roughly modern day processors. This one has 4 cores, 125 watts. Here we have single core, 2 watts. So there's design trade-offs. So you're going to want to build different processors in the same design technology, we'll say, but with very different cost, power, performance trade-offs. This one can decode 3 instructions. This one can decode 2 instructions, so it's a different microarchitecture difference. This one has 64 kilobyte cache, L1. This one has a 32 kilobyte L1 iCache. Very different cache sizes, even though they're implementing the same architecture, or big A architecture. Strangely enough, they have the same L2 size. You know, things happen. This one's out of order versus in order, and clock speeds are very different. And I wanted to contrast this with different architecture, or different big A architecture, and different microarchitecture. So if we think about some different examples of instruction set architectures, there's x86, there's PowerPC, there's IBM 360, there's Alpha, there's ARM. You've probably heard all these different names, and these are different instruction set architectures. So you can't run the same software on those 2 different instruction set architectures. So here we have an example of 2 different instruction set architectures with 2 different microarchitectures. So we have the Phenom X4 here versus the IBM Power 7. And we already talked about the X4 here, but the Power 7 has the power instruction set, which is different than the x86 instruction set. So you can't run one piece of code that's compiled for this over here, and vice versa. And the microarchitectures are different. So here we have 8 core, 200 watts, can decode 6 instructions per cycle. Wow, this is a pretty beefy processor. It's also out of order and has the same clock frequency. Something that can also happen is you can end up with architectures where you have different instruction set architecture or different big A architecture, but almost the same microarchitecture. And this does happen. So you end up with, let's say, 2 processors that are both 3 wide issue, same cache sizes, but let's say one of them implements PowerPC and the other one implements x86. And things like that do happen. That's more of a coincidence, but I'm trying to get across the idea that many times that the microarchitectures can be the same, and those are more trade-off considerations versus the instruction set architecture, which is more of a software programming design constraint.